Gotta move around when you're thinking. And if you're at your seat going, oh, she's making a big deal about it, it's pretty easy. You just might be more comfortable with this kind of representation. It just kind of depends on, it's a different thinking to re-represent the problem using different stuff, but you may have some experience doing that in other courses. It's the idea of doing a U substitution is sort of math specific, but there are other places where you could do that. Just kind of let you take something very complicated and break it, rewrite it in a simpler format. All right, so there's the correct pick for U. U should be x squared plus 3x. If it's a problem where U substitution is going to work, there's only one way it can work. Right? It's not like an opinion thing. X squared plus 3x is gonna be the U that works. Because, and remember, this is now kind of how I'm looking at it. When I'm looking at a problem, and if we were at a point where we were trying to decide if U substitution should work, this is something I would kind of be doing in my head. I would be looking at, do I have a U and a derivative of U in the problem? That's what my AP students have to do when we get to the point where we're doing a bunch of different integrals, kind of all different strategies mixed together, is, wait a minute, how does this one work? Does it have the U du combo? Right. Based on the derivative of what I've picked for U, I can legally replace 2x plus 3 dx with du. And the nice thing about doing that is the fact that then basically makes this part of the integral almost irrelevant. It has to be substituted correctly, but once you figure out that that's the substitution, that this is going to be u to the 1/2 du based on this choice for u, then the du is kind of like a nothing burger. You don't do anything to it. It just sits there. It kind of has just sucked up part of the problem and made it not relevant for us. And so we focus on antiderivative in terms of u. U to the 3/2 divided by 3/2 plus c and then clean up. Two things to clean up. Number one, you know me, nope, let's do this. 2/3 u to the 3/2 plus c, and then this is where I'm always like, what was u? Oh yeah, x squared plus 3x. X squared plus 3x to the 3/2 plus c. If we took the derivative of that, and this is good to, this is when I kind of waited till I was recording before I said this. One of the ways you could check this is take the derivative. Now, you'll have to remember though, when I take the derivative of something like this, I need to use that chain rule thing. So the derivative would be 2/3 times 3/2 times x squared plus 3x to the 1/2 times, chain rule says take the derivative of the inside, and then the derivative of the constant would be 0. Those guys multiply out, and so look at what I get. I get x squared plus 3x to the 1/2 times 2x plus 3, which was exactly what was in the original problem for the integrand, the thing next to the integral sign. So if my answer's right, if my antiderivative is right, and this has been true all along, if my antiderivative is right, I should be able to take the derivative of that antiderivative and get back to what was originally in the problem. Okay. Yeah. No, maybe, sort of, anything. Brian.
So, I mean, I got the answer right because I copied exactly what I did last time. But
Okay.
I don't know when do you know when the derivative of u is just the other part?
When do you know that?
Yeah. Is it always that?
It either has to be there, well, it kind of has to be like that for this to work, right? So for us, if we're just practicing this, I'm kind of giving you a bunch of problems that are sort of designed to work this way. If we were doing mixtures of problems, we would have to look at the problem and kind of see, all right, do I have those components? Do I have a function and its derivative in the problem so I can attack it this way? If you didn't have the pieces set up perfectly, then yeah, you would have to use another technique. So that's why this is like, it's a good technique, but you really have to, like, everything has to be sort of perfectly aligned almost to make this work. Got it? But yeah, I mean, that's what a lot, with the first times through these, that's kind of what you do. Like, I'm just kind of copying, just kind of doing the process. I don't really know, I'm like doing it. I feel good about what I'm doing, but I'm just doing the process, right? Okay. So perfectly onto what Brian just talked about, sort of asked about, is, looking at number 3, you might be like, well, wait a minute. This isn't right because I don't have enough stuff kind of to make U substitution work. But you do. There are ways that even if I don't have a perfect match between U du, I can create a match. So let me show you, that's where the sort of the first variation problem is. Things are not perfectly aligned. And this happens a lot, not just in this style of problem, but definitely this style of problem is one of the ones that comes up a lot, where all I have is one big chunk to a power. So assuming I can use U substitution, because Mrs. Willenbrock said I could, that's really the only thing I can do for U. I mean, there's not anything else there. We always want to get U to a power, so the 4 is never, the exponent never kind of gets sucked into the U. Be careful with saying never, but not as often. And so, but then when I take the derivative of what I've identified as U, the derivative would be 2. Right? Derivative of 1 is 0, and the derivative of 2x is 2. So my derivative is 2. So to make the substitution work, I'm going to need 2 dx to replace with du. So I need this to make U sub work. And I don't have it. Because if I look up at this original problem, I've got 1 plus 2x to the 4th. So I've got u to the 4th, and then I've got the dx. I need a 2 in there. Mathematicians are shady. We have shady ways to get around things. One of the things we can fix a lot is if we need some kind of magic constant, we need some kind of number factor in a problem. I can always kind of put something in and then put something else in to sort of neutralize it. So watch what I'm gonna do. I need a 2. I'm gonna throw times 2 in there. Like, oh, okay, all right. Are you allowed to do that? Well, sort of. I'm allowed to do it if I do other stuff to kind of make it okay. Making it okay would mean not really changing it, just making it look different. So think about that in the concept of sort of canceling things out when we do equation solving. If we wanted to cancel out a multiplying by 2, what would we do? We would, there you go. Most students will say divide by 2 first. You jumped right there. Dividing by 2 is usually the logical next step. And then you're like, well, so multiplying by 2, you can divide by 2 sort of to cancel that out. But dividing by 2 is the same as multiplying by 1/2. So watch this. I'm going to throw a 2 and a 1/2 as factors into this problem. I didn't technically change the problem because a 2 times a 1/2 is a 1 and a 1 times a dx is just a dx. So this is not really a different problem. It's just the same problem that looks different. But here's what happens when I substitute. I have u to the 4th. I know that's a little hard to see because of my green line there. So, where's my highlighter? Oh, she's getting out her toys. Okay. So u to the 4th, right? This part, the 2 and the dx, I'm going to make into du. And this is usually the part everybody hates. There's that 1/2. I got to keep him. He still needs to be there because he's still kind of canceling out the 2, but you don't see the 2 anymore because the 2's hidden in the closet with the du. Right. So that problem, this problem right here, this guy, is the original problem for all intents and purposes. It just looks completely different. You know, but theoretically, if we broke it down, I'm like, okay, that part's u and du is 2 dx, and there's a 1/2, and the 1/2 and the 2 would multiply together. And so if I could undo this, I could take this and I could take him right back here. That's the trick sometimes, is we have to fix things by multiplying in a factor. However, we are only allowed to do this with constant factors. So we can only do this kind of change with a constant factor. Meaning you can't like multiply by an x and then multiply by 1/x to make it work. You can't multiply by like 3c and then divide by 3c to make it work. You can do like a 2 and a 1/2, a 3 and a 1/3, a 2/5 and a 5/2. Because this is always, you know, whatever number you need, you also need the reciprocal of that constant factor. We're going to do a lot with 2's, and so we're going to do a lot of halves, but every single one is not a 2 and a 1/2. All right. After all that thinking and all that magic, I still have to do my antiderivative. 1/2 u to the 5th over 5 plus c. So I would probably make that 1/10, but that's just me. You can leave it as 1/2 and leave the other thing over 5, but you have to change the u back to the x expression. So this is one version of the answer right there. Now, I don't know that I've probably convinced you unnecessarily, because we haven't really proven anything, that this is actually kind of like legal and working and cool. So that's why we're going to go back to the first problem. We're actually going to do this in another space, though. I've thought about these notes. After I started working with them 7th period yesterday, I thought, ooh, I want to change stuff. So this is me doing everything in a different place. Go to example 6, but here's what I want you to do. We're going to actually change example 6, so it's not the problem that's there. It's going to be the problem that we started class with, the 2x plus 3 quantity squared dx. Try that one with a u substitution. Get a u substitution based answer, and then we'll check and see if that u substitution answer and the answer we got at the beginning of class with the 4/3 and everything are in fact the same. So try number 6. Number 6 works just very similarly to number 3.